Welcome to This Explainer. Okay, if you've ever stared at a wall of dense organic chemistry notes and felt, totally overwhelmed, you are definitely in the right place. We're going to take those heavy textbooks and turn them into a clear, visual guide. We'll break down the chemistry of alcohols step by step so we can figure out how these little molecules actually work. All right, here's our roadmap for today. First, meet the alcohol family. Second, naming and making alcohols. Third, properties and reactions. Fourth, ethanol versus methanol. And fifth, the ultimate chemistry tests. Let's get to it. Section 1. Meet the alcohol family. Let's look at what actually defines this fascinating group of chemicals. So what exactly is an alcohol? Simply put, it's an organic compound containing one or more hydroxy groups attached to a saturated carbon atom. It really all comes down to that hydroxyl group, the ROH. The R is just the rest of the carbon chain, right? But that tiny OH part, that is the absolute star of the show. It's the anchor that gives methanol, ethanol, and propanol their completely unique identities. Now, what's really fascinating is how we categorize the siblings of this family. It's super easy. You just count how many carbons are directly attached to the OH-bearing carbon. If it's attached to just one other carbon, it's a primary or 1-degree alcohol. 2, it's a secondary or 2-degree alcohol. And if it's super crowded by 3 other carbons, we call it tertiary. Keeping this 1, 2, 3 hierarchy in mind is actually absolutely crucial for what happens next.
Moving on to Section 2, naming and making alcohols. Let's explore IUPAC Nomenclature and how we prep these.
IUPAC naming can seem super intimidating at first, but honestly, it boils down to 3 straightforward steps. Think of it like a cheat code. Step 1, find the longest carbon chain that contains the OH group. Step 2, number that chain starting from the end nearest to the OH. And Step 3, just drop the E from the parent alkane name and replace it with all. Just like that, a 4-carbon chain like butane logically transforms into butan-1-ol. Now, looking at their chemical lineage, there are 5 distinct ways to synthesize alcohols. Think of these as the essential recipes in our organic chem cookbook. You've got the hydration of alkenes. You can react alkyl halides with aqueous KOH. You can use reduction, meaning either reducing aldehydes to get primary alcohols or reducing ketones for secondary ones. And finally, the Grignard reagent method, which is a really versatile trick for building any class of alcohol you want. Section 3. Properties and chemical reactions. Let's observe how these alcohols behave in the wild. Okay, the real secret behind their physical behavior, like their surprisingly high boiling points compared to normal hydrocarbons, their high viscosity, and the fact that lower alcohols dissolve so perfectly in water, it all comes down to one big phenomenon: intermolecular hydrogen bonding. Because of that OH group, alcohol molecules essentially hold hands with each other and with water molecules. And let me tell you, breaking that grip requires a massive amount of energy. This hand-holding leads to 2 fascinating quirks you need to know for your exams. First, the solubility rule. As the carbon chain, which is the hydrophobic alkyl group, gets longer, solubility rapidly drops off. The molecule basically becomes more like oil and way less like water. Second, their acidic character. Alcohols are weak acids, and their acidity drops as you go from methanol down to tertiary alcohols. In fact, surprisingly, ethanol is actually less acidic than plain water. Crazy, right? Treating this like an exciting unboxing of chemical transformations, we can see exactly what happens when alcohols actually react. Drop an active metal like sodium into an alcohol, and it reacts to form a sodium alkoxide while releasing hydrogen gas. Or combine an alcohol with a carboxylic acid, and you get esterification. Boom, you've created a sweet-smelling ester. And finally, we have dehydration, which leads us to a really tricky phenomenon. Yeah, here's where things get really sensitive. Notice how a tiny temperature shift completely changes your final product during the dehydration of ethanol. If you heat it to 443 Kelvin, it completely dehydrates into an alkene, specifically ethene. But if you control the temperature to just 413 Kelvin, 2 ethanol molecules actually join together to form an ether instead. Literally, temperature changes everything here. Let's map out another major transformation: oxidation. And this all depends on that 1, 2, 3 classification we learned earlier. Primary alcohols oxidize in 2 steps, first to an aldehyde, then all the way to a carboxylic acid. Secondary alcohols, on the other hand, they stop dead at the ketone stage.
And tertiary alcohols, under normal conditions, they stubbornly resist oxidation altogether. They just won't do it. This is an incredibly useful behavior for figuring out exactly which type of alcohol you're dealing with.
Section 4, ethanol versus methanol, a true head-to-head matchup. Let's put ethanol and methanol head-to-head. Now, both function perfectly well as industrial solvents and fuels, but the real-world stakes here are incredibly dramatic. Ethanol is the relatively safe sibling, widely used in medicines and perfumes. Methanol, on the other hand, despite looking almost identical on paper, with just one less carbon, is highly poisonous. It's a pretty stark reminder of how a tiny structural change creates massive real-world consequences.
Section 5. The ultimate chemistry tests. Let's head into the lab and uncover how to identify these molecules. If you ever need to identify these in a practical setting, you'll use the Lucas test, which is a mixture of concentrated hydrochloric acid and anhydrous zinc chloride. Interestingly, the reactions here run completely opposite to the oxidation rules we just talked about. Tertiary alcohols are actually the most reactive here, giving immediate cloudiness or turbidity. Secondary alcohols take a few minutes to get cloudy, and primary alcohols? They show absolutely no turbidity at room temperature. None at all.
We also have the classic Victor-Meyer test. It produces a brilliantly simple, colorful sequence to help identify your compounds. After a series of reactions, a primary alcohol turns bright red, a secondary alcohol turns blue, and a tertiary alcohol remains totally colorless. So between the Lucas and Victor-Meyer tests, you can basically unmask any alcohol class out there. All right, let's do a quick rapid-fire wrap-up of everything we've uncovered today. The core identity of an alcohol is ROH. The Lucas test reactivity sequence goes 3 degree, 2 degree, then 1 degree. And for oxidation, primary goes to acid, secondary to ketone, and tertiary resists entirely. Those are your absolute essential takeaways to lock in. So, armed with the Lucas and Victor-Meyer tests, can you confidently spot the difference between a 1 degree and 3 degree alcohol in the lab? With these chemical tools now at your disposal, you kind of start to view the world a little differently. Next time you use hand sanitizer, pump gas, or even spray some cologne, ask yourself, which sibling of the alcohol family is hiding in there, and what kind of invisible chemistry is happening right in the palm of your hand? Thanks so much for joining me in this explainer. Catch you next time.